Conduction current, as we talked earlier, is different from convection current. And one way we can think about it is that conduction and the conductors obey Ohm's law for moderate fields and voltages applied. So the current increases linearly with the electric field. So in general, current is always charge times the velocity, and it has a magnitude and a direction. But in convection, like acceleration of charged particles, the velocity is given by the acceleration times the time, so it keeps increasing under a constant acceleration, whereas in conduction the velocity is constant for a given acceleration. So we can think of it as a terminal type velocity. Due to all the scattering with the other charges and other atoms, molecules within a material. So most materials fall into this category, and we have special cases of a perfect dielectric when the conductivity is zero, or a perfect conductor when the conductivity is infinite. And in between we have the conductors that under moderate fields and voltages, the current is related to the field by this linear relation where the proportionality is the conductivity given in ohm centimeter. Okay, and it's interesting to see how wide this physical property varies over 24 orders of magnitude. From very good insulators with a conductivity of 10 to minus 17 to very good conductors like silver and copper with conductivities on the order of 10 to the 7 Siemens per meter, and Siemens is the inverse of Ohm. So conductivity leads to this concept of resistance, which is a property of the material that the conductor is made of, the component, but also of its geometry. And that's because Ohm's law, as you can see here, this is called the point or local form of Ohm's law, where we are relating a current density with an electric field. When we are measuring currents and voltages and for a given component, with the current density is related to the total current that is going through the conductor, and the electric field is related to the total voltage drop across, and conductivity is the macroscopic or the component form of that is conductance, and conductance is the inverse of the resistance. So this will depend on the material through the conductivity function, and also on the geometry on how this relates for a given shape conductor. And you can see here an example for a linear conductor, that you apply a voltage V across, and if material is uniform and this corresponds to a constant electric field E times L for a uniform material and uniform cross section. And we can do the same thing for the current. We can integrate this current density that is going everywhere uniformly. We need to integrate it over the whole cross section, and using Ohm's law, that is sigma E times the surface, the differential surface element, and this gives us conductivity times the same magnitude of the field along X times the area of the cross section. And now when we divide one by the other, we get the common linear conductor resistance expression that sometimes is given in terms of conductivity, sometimes in terms of resistivity, which is the inverse. So for any conductor, resistance is defined as this overall macroscopic quantity of the voltage drop through the total current through, and we can find it by taking the linear integral of the electric field to get the voltage, and the surface integral of the current density to get the current. This example shows the same process for a coaxial cable, where we want to measure or calculate the conductance of the coaxial cable from the inner conductor to the outer conductor. So we are applying the positive voltage in the center of the conductor, in the inner conductor. The outer conductor is grounded or negative. And we want to know what is this. This is the current flowing for a dielectric that is insulating this cable, that is not perfect, that it has some finite conductivity. Once you apply a voltage to the inner conductor, there will be some current leaking to the outer conductor, and that's what we want to integrate to find the total current. And also the voltage would be the line integral of the field E. And from that ratio then we can get the conductance of this material. So we can start by expressing the current density. Assuming the material is uniform, the current density is going to be equal to the total current, this total current flowing radially from the center to the outer conductor, divided by the surface where that current is spreading, which is this dashed line here, and the area of that is the circumference times the length of our cable. So from that we can get the field also using the conductivity from Gauss's law. And then we want to express the voltage also in terms of the same parameters. So we are going to integrate the field from A to B or B to A to give us the positive voltage difference. In this case we are applying it at the positive at the center, and the differential length is this vector here, dl, also along, because we are integrating the E along the radius, so this is our dl, and this is the field. The internal product of the unit radial vector is 1, and the integral of 1 over r is the natural logarithm, and this gives us the I 2 pi sigma L times the logarithm. So now, by combining the total voltage and total current, we have this common parameter, which is the total current, that just depends on how much voltage is applying. We can get our resistance, right, which is the voltage divided by the current. So it's going to be the I 2 pi sigma L, the log, and then divided by the current. So we get our total resistance, which only depends on the material, here to the conductivity, and the geometry. It's a coaxial cable, and that information comes here through this 2 pi and the natural logarithm. This is the result of the total voltage divided by total current. And we have our resistance of the coaxial cable. Log B over A 2 pi sigma over L. So the resistance of the cable depends on the cross section, even by the radius A and B, the length and the conductivity. And as we did the voltage drop, it was positive as we wanted, since we are applying the positive voltage in the inner conductor. Joule's law, that in the macroscopic form is the current times the voltage, can also be written in a differential or local form in terms of a power density. We can use a little P, that is the electric field times the current density, and is given in watts per cubic meter. So for a coaxial cable, we could use our current voltage result, where we have the current and we have the voltage in terms of the current, and we obtain the power. And from power density, to get the total power dissipated, we integrate in volume. And for the resistor, the power reduces to this expression too.